Welcome, everybody. Thank you for joining us for this latest instalment of the Europlanet Society webinar series. For those of you who don't know me, my name is Callum. I work on the Europlanet 2024 Research Infrastructure and the Europlanet Society, based down here in Canterbury at the University of Kent in the UK. Thank you again for taking the time out of your day to join us. I'm going to take this moment to promote the next couple of sessions in our series as well, because I hope to see many of you there also. On the 19th of March, we are holding our Early Career Spotlight session, featuring talks from inside Europlanet, from EPEC, and also from external recruitment experts to help you plug into a network of expertise, tools, and tips that you can use if you are an early career, or perhaps you work with early careers in a mentor capacity, for example. And then on the 30th of April, we are going to hold a session about summer and winter schools that will feature examples from within Europlanet, as well as externally, to give you examples on things that you can get involved with, and how you could be involved either as an attendee or perhaps even as an organizer. I'd like to remind as well, these sessions are, of course, for you, the Europlanet Society membership. So if there's anything that you would like to hear about or to speak about, please do get in touch, because the more we can tailor the content to what you, the community, would like to hear about, the better. Super. So our topic for today's session, we're going to hear about the OSIRIS-REx mission and about the results from Bennu. Our speaker today is the lovely Dr. Ashley King from the Natural History Museum in London, here in the UK. Ashley, thank you for joining us.
No,
sorry,
sorry.
Just a moment, Callum. I think we're recording on Otter, but I don't think we're actually recording the webinar itself. So
yes, I'll check that. Thanks, Anita.
Thanks.
I think we are on Zoom. I think we are recording to the cloud, and I'm not sure that Otter will be rolling for this one.
Just wanted to double check. Thanks.
Yes, thanks, Anita. I will make sure that that's the case, so that we can provide this on YouTube for everybody afterwards. Wonderful.
It's recording.
Thank you, Shish. Super. All right. I'll hand over to you, Ashley. Finally, during the session, we will have time after the presentation for some Q&A. So please drop your questions in the chat during the session, or we can address them afterwards. Thanks.
Excellent. Right, let's have a go at sharing this. So thank you very much for the introduction, and thank you for see if I can get that going. Yeah, thank you for the introduction and for the invitation to come and talk to you about this amazing mission, OSIRIS-REx. Hopefully my screen is sharing. Are we all good?
Yes, we can see you.
You can see and hear me. Perfect. Yeah, so I'm a research fellow based at the Natural History Museum, and I am a member of the sample analysis team for the OSIRIS-REx mission, which recently came back and returned to Earth with samples of this amazing asteroid called Bennu. I've just put my name on the front of this, but there are actually over 200 researchers across the world who are currently working on these samples, and this mission came back September last year. We have really only just started to scratch the surface of what we're going to find out about Bennu and what Bennu is going to tell us about how our solar system formed. So, but I can tell you a little bit about why we went to Bennu, why we were interested in carbonaceous asteroids, and give you a very quick overview of what we have found so far studying these amazing samples. So I'm a planetary scientist. One of the big questions that I think most planetary scientists have is how do we go from having this kind of cloud that's full of gas and full of dust, so something similar to this HL Tau system that you can see here in the top left corner, to having a solar system or a planetary system like the one we see today. So how do we make a system that has a central star? How do we have 4 rocky inner planets, and then the gas and the ice giants in the outer solar system, and then the moons and the asteroids and the comets that we see within our solar system? So it's all about trying to piece together and reconstruct the history of our solar system. And the way we try and do that, or at least the way that I try and do that, is by studying asteroids. So asteroids really are the building blocks of our solar system. Most of our asteroids live within this kind of main belt that everyone's familiar with. So that's kind of the belt between the orbits of Mars and Jupiter, we call the asteroid belt. We also have asteroids in other places in the solar system. So we have things like the Jupiter Trojans. We also have a collection of asteroids that we call near-Earth asteroids that have orbits at about 1 AU or so. And most of those asteroids formed right at the start of our solar system about 4.6 billion years ago. And they are, on the orders of meters, tens of meters, a few of them are kind of 100 kilometers or so in size. And so they're small bodies within our solar system, which means that nothing's really happened to them since they formed 4.5 billion years ago. Some of them got heated up a little bit, some of them reacted with water in the early solar system. But really the materials, the minerals, the different textures and things that we see within asteroids are exactly the same as they were as our solar system was forming. And so this means that we can study asteroids, we can try and understand what those materials, what those minerals, what those compositions are. And we're really kind of looking back at time at what conditions were in the early solar system. And so we can take that and try and understand how asteroids formed and then how those asteroids went on to start making things like planets. Ooh. So I'm particularly interested in volatile-rich asteroids. So we have some sort of information for maybe about 1 million or so asteroids, whether that be an albedo or an orbit, or we roughly know its size and its mass. Of that million or so asteroids that we have some information for, about 75% of them are really, really dark, and we call them carbonaceous asteroids. And so the reason we think they're so dark is that they're very likely to contain a significant amount of carbon, and probably also a significant amount of water, either as ices locked up within them, or possibly as OH and H2O bound within the minerals on the surfaces of these asteroids. And so this tells us that these asteroids must have formed in a part of the solar system that was cold. So you had to have had ices, you had to have volatile species like carbon and nitrogen within the materials from which the asteroids were accreting from. And so you're looking at regions in the outer part of our solar system. So most of these carbonaceous, these dark asteroids probably formed, in the outer part of the main asteroid belt, probably around Jupiter and even beyond Jupiter. And some of them possibly formed out towards the Kuiper belt as well. So really interesting bodies. They contain volatiles. Because they formed in these cold regions, they were never really thermally processed. They weren't heated up. So the materials within them are kind of pristine. They take us all the way back to the start of our solar system. And in recent years, we've kind of begun to understand that we probably had giant planet migration taking place within the early solar system. And so as things like Jupiter and Saturn were migrating around the disk, they probably helped to scatter a whole load of those materials that formed in the outer part of the solar system inwards to places like the Earth and the Moon and places like Mars as well. And so we think that these carbonaceous, these volatile-rich asteroids are one of the ways we can help explain why we have things like water and organic materials here on the Earth. So really amazing things. They can tell us what the initial conditions within our solar system were and can maybe help us explain why we have life here on Earth. So we can study carbonaceous asteroids, and most of my work is based at the Natural History Museum, is looking at meteorites that sample these. So these are the dark carbonaceous chondrite meteorites. These are really rare. So we have worldwide maybe about 70,000 or so meteorites in our collections. Only about 5% of those are carbonaceous chondrite meteorites. So we don't have very many of these to work with. Some of the other issues that we have with working with any meteorites is that our collection is completely biased. So we only get meteorites from things that are on favorable orbits. We get meteorites that preferentially survive coming through our atmosphere as they burn up. Some things are stronger than others. And so carbonaceous materials tend to be very fragile, and we don't get very many of them landing on the Earth. And then when they do land on the Earth, we get things that preferentially weather much quicker. And so we tend to lose, if a carbonaceous chondrite isn't found very quickly, we often don't find that carbonaceous chondrite, whereas things like rocky ordinary chondrites or iron meteorites tend to hang around on the Earth's surface much longer. So our collection of carbonaceous chondrites is really biased. It doesn't tell us about all those different carbonaceous asteroids that are out there in the solar system. The other problem we have with meteorites is that we don't really have any geological context for these rocks. We don't know which asteroid they came from in the solar system. So they're just kind of a random rock, which I can study and investigate. But what I really want to know is how that rock fits into all the other rocks that it formed alongside. So this is actually some pictures here. This is the Winchcombe meteorite that fell in the UK back in 2021. And so this is one of only 5 carbonaceous chondrites where we actually saw the fireball as it came through the atmosphere, and we were able to calculate the orbit, which is what's shown on this figure here. And so we know that the Winchcombe meteorite, for example, came from the outer part of the main asteroid belt, but we can't really say exactly which asteroid it came from. So we don't have any geological context for that sample. The other big disadvantage with all our meteorites is they are contaminated. As soon as they come through the atmosphere, they react with the terrestrial environment, and they become modified. Their chemistry changes, their mineralogy can change a little bit. And if you're interested in things like organics and you're interested in things like water, that's a really big problem with studying carbonaceous chondrites is what do we know, what's the extraterrestrial signature and what's the terrestrial signature? So I absolutely love studying meteorites. They're wonderful things. They can tell us a lot about the solar system, but there's some things that we can't learn just from studying the meteorites in our collections. And so that leads us on to sample return. Sample return is very expensive. It takes a long time to get these missions funded and then actually launch them and get to the asteroid or place you're interested in and bring those samples back. So it's not easy to do sample return, but it's absolutely crucial for helping us unravel the history of our solar system. So the reason we need sample return is all those reasons, those limitations we have of the meteorites, is it gives us context for the samples. It gives us an understanding of the geology for where the material came from. So we can go to a known location within the solar system, we can characterize that location, we can collect the sample, and we know how that sample fits into the wider geology of that body. So that's really, really important. I'm a geologist, I want to know how all the rocks fit together. It allows us to ground truth our remote observations. We can't go and send a spacecraft to absolutely every, all the million asteroids that are out there. That's not feasible. But what we can do with sample return is we can characterize the asteroid that we're interested in. We can bring back samples. We can measure them in the laboratory here. We can compare how the measurements in the laboratory match with what we see from telescope and spacecraft data. And so we get a ground truth that we can then apply to other places in the solar system. So that's also a really key reason for doing sample return. We can also do much more complex measurements on samples here on Earth. We build these amazing spacecraft. They often have different spectrometers and instruments on them, and they do amazing science when they're investigating different planetary bodies. But we can also study these samples in the laboratory almost atom by atom these days. I spend a lot of time doing work at the Diamond Light Source, the synchrotron in the UK. It's not possible, it's not feasible to stick a synchrotron on a spacecraft and send it out there to visit an asteroid. So we can just do more complex measurements that aren't possible through remote observations alone. And then we also get really pristine materials. So we, unlike our meteorites, we can keep these things out of the terrestrial environment. We bring them back through the atmosphere in a sealed capsule. We then store them in properly curated facilities. So this is our glove box at the Natural History Museum that we have all our carbonaceous chondrite samples in. And that allows us to study the extraterrestrial signature within these rocks without worrying too much about what may be contamination from the Earth. And then the final thing that's really important for sample return is that, for OSIRIS-REx, for example, we have a 2-year time frame for doing the initial measurements on these samples. But people will be working on samples of Bennu for decades to come. And that's really, really crucial. We can curate these samples, we can look after them and make sure that they're available for scientists in the future who will come along with completely different questions about how our solar system formed. And they'll have the amazing new analytical facilities that we haven't even considered now that can measure these things in a different way than we can do today. So sample return is difficult and it is expensive, but it's absolutely crucial to understanding the solar system. So moving on to OSIRIS-REx. So OSIRIS-REx wasn't the first sample return mission to a carbonaceous asteroid. So JAXA's Hayabusa 2 mission actually brought materials back from the asteroid Ryugu in December 2020. I'm going to focus on OSIRIS-REx, but if people have questions about Ryugu, we were involved and have been measuring those grains as well, and they're amazing. And it's really nice to have samples from 2 carbonaceous asteroids. It gives us a really great comparison that we can start doing between these 2 bodies to understand how they formed. So this is a cartoon of OSIRIS-REx. It stands for origins. So we're interested in a sample that can tell us what the original conditions within our solar system were. Spectral interpretation, that's that ground truthing that I was talking about. So OSIRIS-REx did an amazing job of characterizing Bennu before grabbing the sample and bringing it back to Earth. And what many people are doing now is studying those samples and seeing how they match to the observations that we had from the spacecraft. Resource identification was really important. So Bennu was predicted to be a hydrated asteroid, contain water. So this is something that potentially in the future, spacecraft and missions are going to want to use to maybe make fuel and things. So this was really a crucial part of the OSIRIS-REx mission. Security. Bennu is a near-Earth asteroid. It's not too far away from us, and there is a very, very small chance that in a few hundred years it could hit the Earth. And so one of the things we wanted to do was learn about, what's its size, what are the physical properties of Bennu, what's its porosity, its density, how would we think about, defending ourselves from an asteroid like Bennu hitting us in the future. And then Regolith Explorer the sample was collected from the regolith. This is this kind of top layer of material on the surface of planetary bodies that's been exposed to space and it's been space weathered and noble gases and things get implanted. So it's really interesting to tell us about the space environment. So this is just shows the timeline for OSIRIS-REx. So it launched in 2016. It got to Bennu in about 2018. So this is a near-Earth asteroid. This is one that's relatively close, but it takes a couple of years to get out to these things. It then spent a couple of years characterizing the surface of Bennu in much more detail than we've ever done for any asteroid. It actually went in its first mission to go into orbit around an asteroid. And it had a whole load of instruments trying to understand what the surface composition was and what the properties of that asteroid was. And then after doing that in 2020, actually made this amazing kind of drop down to the asteroid surface. And I'll show a few videos and things from that, and grabbed a piece of that asteroid and then spent 2 years bringing it back. And last September, that sample arrived here on Earth, and we're now entering the sample analysis phase of the mission. So this is just what Bennu looked like as OSIRIS-REx was getting closer in 2018. And then this is what it looks like in all its glory. So Bennu, as I said, is a carbonaceous near-Earth asteroid. It's about 500 meters or so across the bulge. So it's about, so for comparison, Ryugu is about 900 meters or so. So Bennu's about half the size of Ryugu. And what they were kind of planning for kind of shows the need for ground truthing our remote observations, because lots of the telescopic information before, and there was a lot of telescopic information because this was an asteroid that we were sending, $1 billion mission to. So lots of that information had suggested that the surface of Bennu was going to be a little bit like a sandy beach. That's what kind of the size of the materials on the surface were going to be like. And so one of the first surprises that they got when they arrived at Bennu is it's covered in huge boulders. You can see it all over the surface of here. Some of these are tens of meters in size. So it was not this kind of sandy environment, this fine-grained material that the mission team was expecting when they arrived at Bennu. And that posed some challenges for actually collecting the sample. Big boulders, you don't want them anywhere near your spacecraft when you're trying to grab your piece of asteroid. So this is Bennu rotating around. It goes around on its axis about every 4 hours or so. It may not look it in this picture, but the surface is really, really dark. It has a very, very low albedo. And so this is one of the reasons that Bennu was chosen, because we think it's probably going to be rich in carbon-rich or carbonaceous type materials. Its density is about 1.2 grams per centimeter cube, so very, very low density. And its porosity is probably over 50%. So it looks like a solid surface on the top, but actually the interior of this is probably very, very porous. And so this makes us think, and Ryugu has very similar properties, has just as dark, has very low density, very high porosity. And so we think both of these asteroids are what we call rubble pile structures or rubble pile asteroids. So these were probably bodies, with more asteroids we visit, we're seeing this more commonly. They were probably a kind of a first generation of much larger asteroids in our solar system that were then smashed up during impacts. The early solar system was really, really turbulent. And these large bodies, all these fragments kind of scattered out and then started to reaccumulate into these kind of asteroid families of much smaller objects. And so that's what we think Bennu and Ryugu probably were. These are kind of lots of mishmash fragments that are reaccreted together from what was likely to be a much larger parent body in the early solar system. So one of the other surprising things when they first got to Bennu was that, traditionally we often think of asteroids as being kind of rocky objects that don't do very much, and comets being icy objects that when they come in close to the sun, they have sublimation and things, and we have these really spectacular tails, and they look active. And so when they got to Bennu, hopefully you can see in this picture that there was a whole load of particles were kind of spurting or sprouting out off the surface of Bennu. So it's not a geologically dead world. Stuff is still happening on the surface of Bennu. This is really amazing. This is not what we were expecting to see. So behavior kind of similar to what you see, not quite the same, but similar to what you may be seeing in a comet. And I think actually some of these particles would be ejected off the surface of Bennu and actually go out and then crash back down into the surface of Bennu, rather than being ejected completely into space. And the reason probably that this is happening is likely thermal fatigue. So just as Bennu goes around its orbit, it gets slightly closer to the sun and then slightly further away. And so the rocks on the surface are heating up just slightly and cooling down and heating up and cooling down. This potentially is leading to these kind of outbursts of particles from the surface. It could also be that we have micrometeorites and things bombarding into the surface and helping to eject some of this material. So again, really early on, we were getting surprises. We were seeing things on Bennu that weren't really predicted. So as I said, the OSIRIS-REx spacecraft was the first ever mission to go into a complete orbit around an asteroid. It's really difficult. It's spinning very, very quickly. It basically has no gravity. So this is not easy. I'm not an engineer, but these are not easy things to things to be doing around in an asteroid type environment. And what that allowed OSIRIS-REx to do for the first time was collect a complete geological map of the surface of Bennu. So we've never been able to do this for an asteroid. Done it for planets and things before, but never for an asteroid. And it turns out that the spectra of Bennu are pretty homogeneous across the whole surface, and I'll show some spectral things in just a second. But it looks pretty much the same. There are differences in the spectra across the surface, but largely it's pretty homogeneous on Bennu, and it was kind of similar on Ryugu as well. But the main units, the people who've been working on the kind of remote observations of Bennu have split the surface into two different geological units. So we have what's shown in red here is kind of the smooth unit, so where you see fewer of those really large boulders. And then you have the blue regions on here, which is the rugged unit, where you see many more of those kind of boulders. So that's really interesting. We can start trying to piece together the geological history of Bennu from looking at these two different units. So as I said, they collected a whole load of reflectance spectra from the surface of Bennu. And so this is an example of one of them. So the global average, I think. So Bennu on here is this blue, slightly noisy line. And what we're looking at here is the 3-micron region in the spectra, in the infrared spectra. And the 3-micron region is related to absorptions due to OH and H2O bound within different minerals. So if we see this little bump that you can see here, this tells us that we've got water in the surface of Bennu locked up in some of those minerals. So this is really exciting. This is one of the reasons that Bennu was chosen. We thought it was a volatile-rich asteroid. We knew it was going to be carbonaceous, and we thought there was likely to be water in the minerals. So this was great. And you see this feature all over the surface of Bennu. So it looks like it's a hydrated asteroid, is what they were hoping for. Just for comparison on here, that the red and the orange and the green are spectra collected from meteorites in the laboratory, different carbonaceous chondrites, which they're just shown over here. And so you can see these all show these maybe slightly more intense features than we see within Bennu, but they all show these 3-micron features, and we can study those rocks, and we know that they're made up of these hydrated minerals. This is also spectra. So again, Bennu in blue here. This shows the mid-infrared region. We often don't have this spectral region for many of our asteroids. And again, we can see there's a slight feature. Oh, I've lost my mouse. Where's it gone? There's a slight bump here, about 10 microns, between 10 and 12 microns. And you see the same feature in the meteorites. This is very consistent with the presence of hydrated silicate minerals. So the first thing we identified was that the Bennu surface is going to be rich in hydrated silicates, what we call phyllosilicate minerals, and they have OH and H2O bonds locked up in their structure. So this isn't liquid water flowing around on the surface of Bennu. It's not ice. It's things that are locked up within the mineral structure. Another interesting feature that we saw, these are slightly less clear, but there's a couple of, this is Bennu in black. There's a couple of tiny little bumps in here that are really consistent with the presence of magnetite within these surface minerals. And magnetite, again, is something we see quite commonly in some of our carbonaceous chondrites. It's an iron oxide mineral. And like the hydrated silicates, it forms during water-rock reactions. So what this mineralogy is telling us is that Bennu probably formed in the outer solar system. It accreted ices. Those ices got heated up just enough to melt, and they started to react with the rock. And during that process, you start making what we call secondary minerals. So you start making all those phyllosilicates, and you start making things like magnetite. And so this is really exciting for us. It means that these Bennu samples potentially are going to be telling us about water rock reactions within the really early stages of the solar system. The other key mineral that was found on the surface of Bennu that's related to water rock reactions are carbonates. And so if you imagine things like limestones here on the Earth, or the kind of the scum you sometimes get inside your kettles, these are often carbonate type minerals, and these precipitate out of the fluids. So there was liquid water on Bennu, and these carbonate minerals precipitated out. And what's really amazing on the surface of Bennu is that they actually found or could identify veins of these things. So this thing is, it's about 50 centimeters. These are tens of centimeter sized veins. We don't see these in our meteorites, probably because our meteorites aren't big enough to show us this type of veining. But this tells us that there was likely to be, veins of fluid moving around on Bennu, or at least on Bennu's parent asteroid. So we had a hydrothermal system going on within the first few million years on Bennu. And so now it's really key for us to try and find these things in the samples and understand what was going on here. We can use carbonates to piece together things like pH of the fluids. We can actually date carbonate minerals as well, to say exactly when those fluids were moving around. The other thing that we saw in the spectra we knew it probably had lots of carbon, based on the really low albedo, but also we could detect things in those infrared spectra related to things like aromatic and aliphatic carbons, so organic type materials on the surface of Bennu. Another surprise was the detection of some really bright boulders. Excuse me. So not really common, but every now and again you find these kind of bright things on the surface of Bennu. And again, you can collect reflection spectra for these and look at what their mineralogy and what their composition is likely to be. And it turns out these are probably really similar to what we call the HED meteorites that we have here on Earth. These are the howardites, the diogenites, and eucrites. Excuse me. And the HEDs are really interesting because we're pretty sure that they come from Vesta. And Vesta is a much larger asteroid where we had heating and differentiation. It's very much more like a protoplanet. There was melting. Those rocks have been transformed. Then what we call achondrites, they're igneous type-like rocks from volcanoes and things. Not what you would expect to be seeing on the surface of Bennu. So that tells us that there was probably mixing between different asteroids going on in the early solar system. So it's really exciting. And we'll see if we can find some bits of HED within the samples that have come back. So just to summarize what we knew from the remote observations of Bennu, or some predictions based on the remote observations, I guess, is that we were expecting the samples that came back last September to be rich in these hydrated silicates or phyllosilicate minerals. So things like, this is serpentine, very common mineral here on the Earth. Things like magnetite and calcium carbonate. We know from the meteorites, we see all of these in many of our carbonaceous meteorites, and we also see iron sulfides in the meteorites, but these are not possible to detect from remote sensing. But we thought the samples are likely to have these iron sulfide minerals, again forming from fluids on Bennu's early on in Bennu's history. We also predicted that there were potentially going to be exogenous material within Bennu, so stuff maybe related to the HEDs, maybe related to Vesta. Okay, so moving on to the sample. So OSIRIS-REx spent about 2 years or so making that geological map, characterizing the surface of Bennu, and deciding upon a suitable sample selection site. And this was not easy because of all those boulders. And so I think there was lots of debate between the science team about who wanted to, they want to collect the most scientifically interesting sample, and the engineers who want to make sure the spacecraft doesn't crash into the surface of Bennu and doesn't bring any sample back for us. And eventually, there was quite a thorough process, and eventually they came back and decided on this site. This is Nightingale. You can see it's relatively smooth. There's a few big boulders around here, but the region in here is pretty smooth. And this is up near the kind of North Pole on Bennu. This is the sample collection recorded. So this is basically OSIRIS-REx. The spacecraft had an arm on the end of it that came down. And on the end of this arm, this is what we call the TAG-SAM, the touch and go sample acquisition mechanism. So this is the thing that actually contacted the surface of Bennu. So this is the Nightingale site you can see here. And the idea is it's kind of worked a bit like a backwards Hoover. It hit the surface, and then it kind of fired nitrogen to help kick material. And then within inside this, I'll show you in just a second, within inside this is a kind of collector head for storing the material. And so you can see when it touched the surface of Bennu, it made a real mess. You can see all this material being kicked up and going everywhere. And the surface of Bennu turned out to be really, really soft. It went in very, very easily when it touched it. I think they've described it a little bit like if you imagine jumping into one of those ball pits that kids have. They were a bit like that. It just kind of sunk in, and then kicking the nitrogen helped them back away from the spacecraft, back away from the asteroid side. So this is what it looked like when they came back after the collection. So this is the other side. This is the surface of the taxam that touched Bennu. You can see around here these little pads. These are what we call the contact pads. They've kind of got little fibers on them. The idea was they were just going to grab little particles off the surface of Bennu, and then most of the material went into this central part here. This is where all the collection went into. And unfortunately, what happened, or maybe fortunately, there was a lot of material. You could see it from those videos, kind of forced into the collection head, and you can't quite see it in this video, but a particle got kind of lodged. There's a mylar flap that runs around the inside of here, and a particle got stuck. And so when they backed away from the spacecraft, they very quickly realized that material was starting to flow away out of the taxam. So they had to make a decision to stow this. They'd hoped to spin the spacecraft to actually try and work out what the mass of the sample was, and they decided not to do that step and just get this stowed as quickly as possible into the sample return capsule so that all the material was safely stored and could be brought back to Earth. Cool. And then that's what happened last September, end of September 2023. So this is a little video. So the OSIRIS-REx spacecraft spent about 2 years getting back to Earth, and then it kind of, as it flew by, it dropped off the sample return capsule. So hopefully this will play again. There it goes. So OSIRIS-REx, the spacecraft, has now gone on to a second mission. It's going to be not a sample return mission, but it's going to go and visit another asteroid and characterize it. And so on its pass by Earth, it dropped off the sample return capsule, which goes here. This is an amazing video. This limb, this is actually the Earth. So this thing was dropped off, started making its trip back down to Earth September 24th last year. Oop, let's go through. Oh, I've skipped ahead. Let's see if this one. So this thing came back through the atmosphere, has all these parachutes that come out to try and slow it down, stop it crashing into the Earth's surface. Is not what we want. We don't want to mix all that pristine asteroid material and contaminate it with the surface. It landed in Utah. So this is the Utah desert, and here you can see it. This is the parachute. This is the sample return capsule. Then in just a second, you'll see the moment it makes contact with the ground, because the parachute will. There we go. So this told us that it safely made this journey down, and you know, it was blowing around a little bit. It wasn't spinning or anything as it came through the atmosphere. And then we have this beautiful shot of it landing. It made a pretty much near perfect landing in the Utah desert. There's no evidence of it rolling around on the surface or being flipped or you know, thrown around at all. It landed very close to a road, which made it very easy to get to. Wasn't completely in the middle of nowhere, although they flew helicopters out to go and collect this. And so this is the sample return capsule after its 7-year journey in space. You can see looking in pretty good condition, apart from that black kind of crust on the outside when it's come back through the atmosphere. So the team went and collected that really quickly from Utah. It was taken to a temporary clean lab out there in Utah where they kind of opened up the sample return capsule and things and had a quick look at what had come back from Bennu. That was then flown down from Utah to Johnson Space Center in Houston, where they have a specially built curation facility just for the OSIRIS-REx samples. And so it got to Houston on the Monday, and was Monday afternoon, just after lunchtime, I think, and very quickly went into this basically specially built glove box for storing the samples. And then they took the lid off of the capsule here. So this is the taxam. This is the collector that you can see here, the end of that arm that I showed in the videos. And maybe you can see within here, there's some kind of fine black powder, and particularly around these edges as well. This was very exciting to watch. When they lifted this lid up, we could see that there was material on what we call the avionics deck. And this was expected. This wasn't stuff that was completely, wasn't everything leaking out of the sample. They were thinking the material, particularly after seeing the contact with the asteroid, how much stuff was thrown out. They were predicting that there would be material on this avionics deck. So this is, again, a close-up So already we had loads and loads of asteroid, loads of Bennu material available for us to study. And so the plan was we actually had a kind of quick look analysis team, and I was really lucky to be part of that quick look team over there at Johnson Space Center when this capsule came back. So there's the whole team. We were given a small amount, so the curation team at Johnson Space Center swept up some of this powder, took some of this, swept it into some little vials for us, and handed it off to the quick look team a day or two after it had arrived. And we were basically tasked with spending 3 days using electron microscopes, X-ray techniques, infrared spectroscopy to try and get a really first impression of what material we had brought back. Did we have the things that we saw from the remote observations, and how are we going to work, or how, as I said, there were 200 people waiting to get their hands on this. So kind of what's the material have we got, and what's the best way to start analyzing that material? So it's one of the very first pictures that the quick look team took of one of the Bennu samples. So just to give you an idea, there's a scale bar. This is 250 microns. So we only got a very tiny, tiny fraction of these things. But this was just amazing to see this for the very first time. It's really, really dark. Sometimes doesn't show up very well in the photos, but it's really, really dark. And you'll see there are some little speckly bits and things in there as well, and something we see in Ryugu particles as well. So not completely pitch black. Some interesting minerals and stuff going on. My job was to do the X-ray diffraction. So I was given nearly 100 milligrams of powdered Bennu sample. I mean, it was very fine grained. We didn't have to powder it. It was basically a powder of Bennu. An X-ray diffraction can tell you very quickly what minerals you have within your sample. And it's a relatively straightforward measurement, not too much messing around with sample preparation or vacuum pumps or anything like that. And so we got handed this little vial of material and told to go away and be productive and come back and tell us what's in that sample. And so this is a very noisy figure, and I don't expect everybody to take all the information in. But I guess what I wanted to say was that we could work out from the X-ray diffraction very quickly that the main mineral, or the main minerals that we see within the Bennu samples, are those phyllosilicates, the hydrated silicates. They're there at probably about 80–90% of the Bennu sample. At least what we've been studying so far is made up of these phyllosilicates. And as I said, these are things that formed through water rock reactions really early on in Bennu's history. And then we see things like magnetite. That's there very clearly. We see iron sulfide, and we see those carbonate minerals like calcite. So the mineralogy that we've managed to establish so far for those Bennu samples matches really, really well with what those remote observations were predicting. So that's really great. We went to an asteroid. We got what we were hoping to get from that asteroid. We also, as I said, we did a whole load of work on electron microscopes, actually imaging the particles and looking at the mineralogy within there. So they backed up the XRD data really nicely. So these are a few examples. These are, you can kind of see some tufty structures to these. It's a little bit like asbestos in some places. Excuse me, sorry. So these are those clays, these phyllosilicate type minerals that make up most of the rock. And then we have these really beautiful sulfide, really, really gorgeous euhedral crystals of iron sulfides. And that's what some of those speckly things that you could see in those dark fragments I showed you were. Then magnetite is very, very common within all these samples so far, and it forms, magnetite's interesting. It forms lots of different morphologies related to kind of how much iron is in the solution and things. So it tells us about what the conditions, what the water composition was from what it was forming from. So you get these beautiful kind of framboid, what we call framboidy magnetites, and these plaquettes and type stuff. And we have lots and lots of gorgeous images. I can't show you all the images we've taken of the mineralogy of Bennu so far. This is interesting. So this is a particle Bennu that was pressed flat and then was analyzed using ultraviolet light. And so this is the particle, it's the optical image of the particle, and then this is the UV kind of response in this picture. And you'll see it's mainly, it looks a bit like a starry night sky or something. And most of it's this kind of bluey color, and then you'll get these bright spots everywhere. And those bright spots, some of those are carbonate minerals. So we see carbonates within the sample very nicely, and that matches really well with what we were seeing on the asteroid surface. Some of these are also carbonaceous minerals, so they're kind of like organic or carbon and nitrogen rich patches. And yeah, we see things like this within our meteorites. We often call them nanoglobules. These are really common within the Bennu samples we've looked at so far. And Bennu is so far the measurements, we're looking at about 4 to 5 weight % carbon within the Bennu samples, which is perfect. It is exactly what the organic chemists wanted to do. And there are lots of people who are now very busy trying to understand what the composition of the organics and what the nature of organics are within these samples, and how do they compare to the meteorites we have in our records. And as I said, these are pristine samples that haven't seen the terrestrial environment. They're not contaminated. They're really telling us about what the organic species were in Bennu. So this is the picture. I've done a couple of these talks since we got the samples back, and this is the picture I was showing to begin with. So this is the TAGSAM head, and these are these contact pads, and then this is the material. So you can see this is, I think, where the stone that was stuck under the Mitre flap was. And so there was you may have seen in the news that we got the avionics material off the avionics deck for the quick look very quickly, and then they had to get the main sample out of inside the TAGSAM, and two of these screws, you can this top plate is supposed to lift off, and unfortunately 2 of them are kind of cold fused in space, and so they couldn't get all the material out of the TAGSAM initially. They managed to get some of it out by pressing down on this Mitre flap and getting out. I think they got about 70 grams or so out from the TAGSAM early on. And then just recently, you might have seen last week, they announced that they've now got all the material out of the TAGSAM head. And we have 121.6 grams of Bennu to be working with. So the mission requirement was about 60 grams was the minimum requirement. We've got double that amount of material. To give you an idea, Ryugu, JAXA's the Hayabusa 2 mission brought back about 5 grams of Ryugu. So we've got plenty of material to be working with. It's an absolute dream to have so much. We can, you give me a millimeter particle, I'm pretty happy for the next 2 years, but we've got much more than that. And that's crucial for the science we want to do now, but it's really crucial for the science that we want to do, or people might want to do in the future. And as I said, this is all being curated and looked after at Johnson Space Center and a few other places. And this material is going to become available for the community to start analyzing in the not too distant future. So yeah, we've just about started working on these samples. It is really early days, and look out, there'll be lots of exciting science coming out from these materials. So I think it's a good time for me to stop. So yeah, just a reminder, carbonaceous asteroids are, well, by far and away my favorite asteroids. They are the leftover building blocks of our solar system. They tell us what materials were there at the start of the solar system, and they can tell us how those materials came together to start making planets, and in particular, how we make habitable planets like the Earth. We have just received samples, 6 months or so ago, from the OSIRIS-REx mission, which went to the carbonaceous asteroid Bennu. And the spacecraft predicted we were going to have hydrated minerals, we were going to have carbon, we were going to have organic molecules. Really early analysis of the samples suggests that we've got all of that and plenty more locked up in these things, and they're going to keep us very, very busy. And yeah, there's over 200 people at the moment who are in their labs, pretty locked in there 24/7 at the moment, working on these samples. They're really, yeah, it is a treasure trove really for planetary scientists to understand, as I said, all the way back to the beginning, how do we go from that cloud of gas and dust to having the planetary system that we see today? Yeah, and I will stop there. Thank you very much.
Thank you, Ashley. That was absolutely fantastic. I absolutely loved how you showed the videos there. It really set the events within a narrative and made it really very compelling. So thank you again for taking the time out of your schedule to join us and to talk.
No problem. Thanks for having me.
I'd invite everybody watching to put questions in the Q&A section if there's anything that they would like to ask, and then we can either read out from the Q&A and then we can answer them, or if the question requires maybe a more complex conversation, we can promote you to panelists so that you can speak with your mic on. So yeah, we have some time for questions. I'd love to hear those. A question that I had actually was about how you got involved with OSIRIS-REx and what your background was beforehand.
Oh, that's a really good question. So I have been working at the Natural History Museum now for, well, over 10 years, pretty much. And when I joined the museum, it was to work on a project using X-ray diffraction to understand the mineralogy of carbonaceous chondrites. And one of the big challenges with carbonaceous chondrites is they are very fine-grained. So most of the minerals in there are less than a micron or so in size. So give you a feel, human hair is about 100 microns in size. So these are very small. And so it makes it challenging to study them using even electron microscopes and optical microscopes. And so X-ray diffraction allows us to do some things that we can't do in other ways to work out what minerals are there and in particular, how much of each mineral is there. And then we can use that to reconstruct things like how much water, how much water was there, what was the water rock ratio, what were the conditions of alteration. So that was kind of what I've been doing for 10 years or so now. And then obviously you get good at doing stuff with carbonaceous meteorites, and they're going to bring back the predictions were this was going to be a lot like the carbonaceous meteorites that we have in our collections. And so we can say, look, we can do these amazing measurements. We're really familiar with handling these types of samples. They are very difficult to handle. They're very soft. They're very fragile. You can't just, it's not the same as just picking up a piece of basalt on the Earth at all. And so I got involved, and I've been officially sort of been involved in the mission on and off for several years, but officially I joined just over 2 years ago as what they call a participating scientist. So I had to write a proposal and was selected. And then, the X-ray diffraction is something they were really keen to do very early on because it tells you what the bulk mineralogy of the sample was. So I was like, I'll very happily come over to Johnson Space Center and do that for you. Not a problem. So yeah, it was amazing. It was incredible to be there I was there for a couple of weeks, sort of in the build up and the lead up. And yeah, I just see it. I was there when they opened the lid up and we could see all that powder. And it was just like, it worked. It worked.
That must have been amazing. Thank you.
Yeah, it's incredible. Yeah.
We have 3 questions in the Q&A. The first one is from Gareth, who asks, is there any indication of the heterogeneity, I hope I'm pronouncing that right, of the sample above the millimeter scale? And is there any indication the light colored material has been sampled?
So it is, most of what has been looked at so far have been partly because the TAGSAM head was locked or couldn't get into it very easily, is fine-grained particles that are on the order of a millimeter or so. And they are pretty heterogeneous. And what will be happening and is starting to happen within the material within the TAGSAM, so if I go back, it's not so clear. These are centimeter scale bars on here. So there are particles in there or grains in there that are centimeter scale. So pretty big for us. And so they're now going to start processing those things, and they will be very heterogeneous. I'm sure they will. But even at the millimeter scale, we're seeing quite a lot of variation between the different particles that we've been looked at so far. But we've looked at a handful. We're only just getting going with this.
Thank you. Our next question is from Simon, who asks, considering that the material on the surface can be deposited gradually in time after impact, did you find any differences in composition within the sample studies so far?
So that's one thing that they'll be trying to do with the contact pads. So the sample that was collected from the main sample in the TAGSAM, it was obviously kind of mixing material from below the surface. And that's interesting because it's kind of shielded from the space environment. But the material in the contact pads and those little fibrous things, the idea is that they really will be particles just from the top layer of Bennu. So yeah, I don't think we've done enough work to say anything at all about whether there are differences between there, but it's absolutely something that people will be working on. Things like space weathering and stuff changes the surfaces of asteroids. We know from Ryugu for Ryugu they collected material. So they collected material from the surface. They did 2 collections on Ryugu. It was amazing. So they collected material from the surface, and then they deliberately fired a little pellet, a little kind of projectile into the surface to make a crater, and then sampled inside that crater. So we have what's called chamber A particles and chamber C that sample different depths. And there are subtle differences between those things. So and so we'll be still working out what's going on in Ryugu, and we'll be doing the same for Bennu, and then we'll be trying to see how these 2 asteroids relate to each other.
Super, thank you. Our third question is from Thomas, who says, thank you for the talk, really interesting. What do you think about the potential for complementary insights from OSIRIS-REx, Lucy, Psyche, and other missions to asteroids of different types?
Yeah, I mean, that's what we want to do. We've been to Bennu, we've been to Ryugu. They're not exactly the same materials, but that's 2 asteroids out of a million. So what we're trying to do is use these samples to help ground truth those remote observations, so that when Lucy arrives, we can try and that's not going to be a sample return. It's just going to be remote observations, but hopefully through the work that we can do with Bennu and Ryugu, we'll be able to interpret those remote observations in a better than we can now. And it's absolutely, that's like one of the questions for us is how do Bennu and Ryugu relate to each other? How do they relate to other near-Earth carbonaceous asteroids? How do those relate to the ones in the main belt? The Lucy's going to Jupiter's Trojans, which are thought to be potentially were Kuiper belt objects. So how do they relate to each other? It's yeah, we got so much work to do. So, and Psyche is interesting. Psyche is thought to be an iron asteroid. So it was probably a much bigger. It was probably a protoplanet that melted, and it had an iron core, a bit like the Earth, but it solidified and got smashed up. That's going to be an amazing mission. That's going to tell us something completely different. So that's really going to tell us about how planets are forming. But one of the interesting things I think with Psyche is that they have detected that 3-micron feature on Psyche. So, and that's not something you would expect. So that points to there being ice or water-rich minerals on Psyche, which is not what you'd expect on a big lump of metal in space. So every one of these missions, we have some idea about what to expect, but until we get there and see these asteroids up close, we have absolutely no idea what's going on. So yeah, we're really excited. I mean, we've been so lucky with asteroid exploration in the last few years, and yeah, really looking forward to Lucy and Psyche. And we have MMX hopefully launching in the next year or two, which is going to go to the Martian moons, Phobos and Deimos, and they look an awful lot like carbonaceous asteroids. That's going to be one of the things they're trying to test is how do they fit in with carbonaceous asteroids, or are they moons around Mars? So
amazing. Thank you, Ashley. We have 2 more questions, actually. The next one is from Shushmita, who asks, how do the mission leads decide what experiments will take place in recovered samples and how much material will be sent to investigators? Is there an application process, or are all activities decided from the outset of project planning?
So for OSIRIS-REx, there are you can go and find this. It's on the arXiv somewhere. There are a whole set of hypotheses that we are testing. So it's things. So some of that is testing what the spacecraft observations told us. So are there hydrated silicates? We can say yes now. Some of it's about what were the initial conditions in the early solar system, what materials were there, how do those materials react with each other. So there's I can't remember exactly how many, but there's a huge number of hypotheses that the OSIRIS-REx mission is aiming to test. So that's the starting point. And then from there, it's which measurement can help you answer that, which sample can help you answer that. So it's really being driven by those hypotheses, which is really interesting and quite a fun way to do it. And it's the way it should be done. The amounts of sample, I can't remember exactly how much sample is going to be distributed in the first. Yeah, I can't remember, but it's not very much, but it's plenty for us, if that makes sense. It's going to be more than enough to keep us very, very busy. Yeah, and then there will be what Johnson Space Center, the curation team are doing, are making a catalog. And then that will become available at some point in the next few months this year, I think. And then, as I understand it, it will be an application process. So you say, I want that specific sample, and this is my project, and it'll probably, I imagine it will go through a peer review, and they'll select the best projects, and that's how samples will be allocated. But yeah, the breakdown, exactly how much mass is being used is I can't remember exactly. But there'll be plenty kept back.
Fantastic, thank you. Our final question is from Neve, who asks, based on the initial analyses and similarities to Ryugu, is the initial finding that Bennu is more CI type rather than CM type carbonaceous chondrite?
Yeah, so it's an interesting question because we're trying to keep out of saying it looks just like a meteorite because, as I said, our meteorites are completely biased. They don't tell us everything that's out there. And also, it's very early days to say it looks like that group of meteorites or it looks like another group of meteorites. I would say that it does look, so far it looks fairly similar to the CI chondrites and looks very similar to Ryugu. And that's really interesting because that's maybe not what the remote sensing was suggesting to us. So it predicted lots of hydrated. The remote sensing suggested it was maybe going to be more CM-like. But it is really early days. So I wouldn't jump on saying it's a CI chondrite-like material, but yeah, but not too different. And we definitely have found things in there. I can't talk about everything that's in there, but there are some things in there that maybe we don't see so much in meteorites or have seen in the Ryugu samples.
Amazing, thank you. Fantastic. Well, that brings us to the end of our Q&A and to the end of our session. I just want to extend a thanks again to Dr. Ashley King for joining us and for giving a fantastic presentation and for fielding our questions as well. We really appreciate it. That was fantastic. I'd like to encourage everybody as well to join us for our next sessions on the 19th of March for our Early Careers Spotlight, and on the 30th of April for our Summer and Winter School session. Again, if you have anything that you would like to raise, either to talk as part of these sessions or something you'd like to particularly hear about, we would love to hear from you. We'd love to have your suggestions. So thank you, everybody, for joining us, for taking the time out of your day. And I hope to see you all again very soon.